I have a very lousy microphone today, so please excuse my problems that I'm going to have here. We're going to be talking today about entropy and free energy. First, our objectives. We will be talking about the two characteristics of spontaneous reactions. We'll talk about the role of entropy, and of course, we'll define and discuss entropy in greater detail. And we will talk about two factors that determine whether a reaction is spontaneous or non-spontaneous. And we will talk about the Gibbs free energy calculations. FYI, as a heads up, the Gibbs free energy calculation is, of course, included on your periodic table. Many chemicals and physical processes release energy. Those that release energy can use that energy to do work. We can use that energy to do work in a car. We can use that energy to do work in a cell phone. If you have light coming on, there's different ways to define work. The easiest way to define work is force times distance. So if your work is used to apply a force that moves something a distance, that's free energy. Free energy is energy that's available to do work. That's the term free energy. Because we have free energy, that is not a guarantee that work will be done efficiently. This is an older slide. I think that cars' engines are probably more efficient than this now, probably maybe up to 35-40%. We use the energy from burning our fossil fuels. Most of us are still using fossil fuels to propel our car. So 70% of the heat from our car is lost to, see what color, no, that didn't work. No, none of those work. Is lost as friction and waste heat. No process can be made 100% efficient. Living things, which are among the most efficient users of free energy, are seldom more than 70% efficient. So you yourself run in the ballpark of a 70% efficient machine. Spontaneous reactions. I don't know if I can get this over, if I can move this over here or not. I can't. We can get energy from a reaction that occurs, not just theoretically. Let's consider this reaction right here. This is a reaction. It's a balanced chemical equation. It's the reverse of combustion. And experience tells us that this reaction does not tend to occur. It happens in the reverse direction. So we're not going to get any ability to do work out of this reaction. When we're talking about how we split up or classify chemical reactions, here's another way. We can divide this into two groups: equations that do happen and equations that do not happen, or at least do not happen efficiently. Sometimes we can put stresses on a system that force something to react. Now, this is just one of many ways. I saw something earlier that gave me a way to, I'm not going to find it. One of many classification systems. Those that do occur, the more important group for us, are what we call spontaneous. A spontaneous reaction occurs naturally. A spontaneous reaction favors the formation of products. So it proceeds right. A spontaneous reaction proceeds forward. Proceeds this way. They produce substantial amounts of product at equilibrium, so they favor the products. That means they'd have a equilibrium constant greater than 1, and they release free energy. The Dr. Cotton example is a fireworks display. If we contrast that to a non-spontaneous reaction, these do not favor the formation of products at specified conditions, so they do not give substantial amounts of product at equilibrium. I don't love this. You can take a moment. I'll just stop for a moment. And you can read that. I don't love that example, but it's fine. Spontaneous reactions. A big misconception. Spontaneous and instantaneous. Spontaneous simply means a reaction will proceed. It doesn't say anything about how fast. Instantaneous means it's occurring very rapidly. Spontaneous does not necessarily occur rapidly. It might take 20 years to react. An example would be sugar plus oxygen yields CO2 and water. This happens, but it would take thousands of years for us to lose a bowl of sugar to this spontaneous reaction. Now let's talk about entropy. This is abbreviated with the letter S. Entropy is a measure of disorder. I like to tell students that I am an example of entropy. We measure entropy in units of joules per mole K. I'm going back up here. There. Joule per mole K. And I'm going to write that here so you can see joules per mole K. That means Kelvin temperature, of course. Now, when it says there are no negative values of entropy, what that means is there are no negative values in our S that we look up. When you look up a table of entropies, we look up a table of entropies, every one of your entropy values will be positive. That doesn't mean our delta S will be positive. Law of disorder states that there is a natural tendency for systems to move to the direction of maximum disorder. Everybody uses this example. Your room never ever cleans itself. My room never cleans itself. An increase in entropy, so if you increase entropy, let me write if entropy increase. This is favored. That's a favored direction. So a decrease in entropy, as entropy goes down, that is not favored. The reaction does not want to proceed. Here's some examples from an old text of entropy, how we can increase entropy. Solid, liquid, and gas. You can see that the gas has the greater entropy. We increase entropy if we have more surface area. We increase entropy if we have more product particles than we do reactant particles. And we increase entropy when we heat something up. So enthalpy, which we represent by delta H, and entropy, which we will represent by delta S, work together to determine spontaneity. So delta H, enthalpy, is favored when it decreases the energy. That means an exothermic reaction with a negative delta H, because that decreases, is favored. And an increase or a positive delta S is favored. Low battery, excellent. These are the two drivers to every equation. If they both agree, a reaction will be spontaneous. If they're both favorable, and we'll look at a slide that shows us this in greater detail, if they're both favorable, we'll have a spontaneous reaction. If they're both non-favorable, it'll be non-spontaneous. So both the size and direction of enthalpy and entropy changes determines whether a reaction is or is not spontaneous. Excuse me. All of a sudden got a tickle in my throat. If both of these drivers disagree, then we'll use Gibbs free energy as we'll do an equation. Again, it's on your periodic table. And that will help us decide at what temperature a reaction will be spontaneous. It will be spontaneous at some temperature. Here's our Gibbs free energy, and this didn't work very well. It's delta H minus T times delta S, where T is Kelvin temperature. So if delta G is negative, then it's spontaneous. This is important. A negative G is favored. That's spontaneous. A positive G is non-spontaneous. That's important. It's sometimes a little counterintuitive. So if entropy and enthalpy don't agree, we do our equation, we calculate the Gibbs free energy, and we find out the reaction will occur. If the Gibbs free energy, we can also use the Gibbs free energy to find the temperature at which a non-spontaneous will become spontaneous. So this is an important slide to look at. And you'll probably want to go and look at this somewhere else because this is an important slide. These are all the conditions in which we have a spontaneous reaction. And my battery's low, so I can't really go through each and every one of these now. So these are endothermic reactions. We have an endothermic reaction, and we have so that's unfavorable. And the entropy is favored. But when we look at the magnitude of our two arrows, when we look at the magnitude of these two arrows, we end up with a heat is absorbed. Okay, that will be an endothermic reaction. So here we can see they're both going in the same direction. This is favored when we have an entropy increase and a heat released. Down here, they're both entropy decrease and an endothermic reaction. So this would be non-spontaneous. And you can look at the different combinations here. And this is a really good slide to study. Again, I'm losing charge. Okay, so this is a really good slide to study. I have not done any problems yet. These are not hard problems to do. We do have a worksheet, and I'll try to get to that and get a slide for that. If not, I've got an answer key on the front bench.